Yeah, good evening everyone. Switch on your cams. Let's start off. Hope everyone has tried the homework problems. Let's see the answers. I get the first one. Other scams on? So in this, what we do from the center, at an angle theta, take a small d theta. So on this strip, the force would be acting this way, which is s into the length is r d theta into 2 times because there are two surfaces. Now, if you look at the symmetries here, only the vertical components will cancel. Vertical components will add up and the horizontal components will cancel out. Similarly, you can take one more here. So the forces would be like symmetry. So F net on the frame will be integral 2s r d theta ka sin theta component. The horizontal components cancel out. You can do, if you want, you can take I cap also and add it up, but they would cancel out. Theta goes from 0 to pi. This will be 2s r integral sin theta d theta. You end up with 2sr, that would be minus cos theta limit 0 to pi. This would be 4sr. Check it out. And this gives you a pretty interesting answer. If you see the answer there, we have a concept called projected length. Remember projected area? Quite a useful concept. This is the second time you're seeing this projected thing. So projected length is basically a line which makes an open curve into a closed surface, closed curve. Quite a useful concept. That means you take any random amoeba shape from point A to point B. So just join the line AB here. And if you have a soap film inside, surface tension is the force on the curved wire is given by surface tension into length of AB into 2 times, because there are two surfaces. This LAB is your projected length. So if you see in our question, what we did, we got a semicircle of radius r. The projected length was 2r. Basically, you have to make it a closed figure. Just like projected area, we also have this projected length. So the force on that semicircle would be S into the projected length 2r into 2 for two surfaces, which is 4sr. That's what we got the answer as. There was a question like this in the exam. They said there was a frame like this. This was A, this was B, this was A, this was C. And they said this entire frame inside there is a soap film. The question was find the force on the frame. What is the answer for this? Yeah. You can simply take the projected length for this guy would be this with the projected length. It doesn't matter what is the shape you take. That A, B, all those are useless actually. So simply the force on this thing will be S into C into 2 times. Easy. But remember, the only problem is this is valid only when S is constant. Basically, the force per unit length should be constant. Please check it out. Yeah, right, Ishan, Anusha, Aryan, got it.
So this means basically when they've not given a function of s, right? Like they've just given a number.
They just S is a constant.
Yeah.
Now, what about the second guy?
Sir, can you show the page again?
This one?
Yes, sir.
Clear? Next thing. What about this thing? The second part? Now, here S is not constant. How do we do this? There are two ways you can do. One, you can directly do a double integration and finish it off, or we can actually split this into two parts. Let's see both of them. So when you have taken this curve, at any instant, if you choose a small section, again, I'm exaggerating the figure here, this can be divided into dx and dy. Basically, this is your length ds. So ds bar is dx I cap plus dy j cap. So force on that small section will be surface tension into ds, s into the ds. A square, b square. Let's see how that works. Into 2 because there are two surfaces. Should I take it as dl? This s is already there. Right. So this is a force on that small arc. So force on the curve will be double integral because we have both x and y. This guy will become 2 s naught by ab x square plus y square, and this vector would be, now be careful here, the force now the on that component dx. So on this component dx, the force is this way. On component dy, the force is this way. Meaning the horizontal component, the horizontal length is responsible for the vertical force. Basically, this is I cap. So you have to be careful here when you take the force. So dy will give you the I cap component minus dx will give you the j cap component. I hope, is that understood? And here x will go from 0 to x will go to a, y will go from 0 to y will go to b. Since x and y are independent of each other, when you integrate x, keep y is constant. When you integrate y, x is already done by here anyway. So let's integrate that first x ka thing. So y will go from 0 to y is equal to b. Let's bring all the constants outside. 2 s naught by ab. This guy will become integral x square dy plus y square dy I cap minus integral x square dx plus y square. Actually, I can split it up separately. Wait, I shouldn't write like this. Let me separate it out. 2 s naught ab x square plus y square dy. This is I cap. This limits will go from y goes from 0 to y goes to b plus 2 s naught ab x square plus y square dx. This guy would be minus j cap this limits will go from 0 to a. Yeah, this is the right thing. This will be easy to integrate. But there is a y also stuck inside. This is not working out. This double integration will have an issue. Let's see. Let's find another way to do this. Okay, let's split it like this. That will be a better way. So if you see all these vertical components, right? Keep your mics on mute. Let's not use double integration. Let's do it normally. See, another way to do this thing, right? If you take this horizontal and vertical, we will try that also. So if you take this full curve, then we'll have three forces here. This is your fx, this is your fy. So on the total curve, we can say F net is nothing but the force on the curve plus the horizontal force Fx plus the force on the vertical Fy. Total should be zero because the net force on the frame is zero because the whole thing is internal. So therefore, we can say the force on the curve so when you add all these forces, the net force cancels out. Minus of F curve and this thing. So basically, if I can find this force and this force, my job's done. So you can split the problem into two parts. So for Fy, you're finding the force on the horizontal line. So at a distance x, take a small section dx. So on this, the force will be dfy. So Fy will be integral 2s dx. Now here, remember this thing. On this line, if you observe it, the y coordinate is 0. On this entire line, the y is 0. So this would be 2s0 by ab x square y is 0 into dx. This is easy. So this would be 2s0 ab, that would be x cubed by 3, so a cubed by 3. That would be 2s0 a square by 3b. And this direction would be j cap. Similarly, you can do this on the vertical one. This vertical line, where you're going from a to 0 to a to b. So on this, at a height y, take a small section dy. On this, the force would be this way, fx. So fx would be integral 2s dy. This would be 2s0 by ab. Now remember, on this thing, the x coordinate is constant. So this would be a square plus y square into dy. Y value will go from 0 to b. This would be 2s0 by ab. That would be a square b plus b cubed by 3. This would be minus I cap. Please check. You're getting what we did? What we did, I'm saying this entire force on this curve plus force on this line and the force on this line, because the whole frame, right? The SO film is at rest. The total force should be 0. So force on the curve should be equal to the force on the two vertical and the horizontal line. So I can find this line easily and I can find this line easily because I know x and y coordinates. So once I got this, I can substitute there on the curve and I'll get the answer. Check it out. This is double integration also, how that works. So you have to take x and y both at the same time. I think I wrote the first one right only. But everyone got the steps. How to split this into horizontal and vertical. You can write this equation because the net force on the frame is 0. Why? The SO film is at rest. Clear? Going ahead. I want to check the double integration thing also once. Let me check that also. So on this, if you take a small piece, dl bar dx and dy, the force on the curve should be double integral x goes from 0 to a and y goes from 0 to b to s naught by ab x square plus y square dy I cap minus dx j cap to s naught by ab. That would be x square plus y square. Just wondering, will this work or not? X square plus y square dx j cap. This has a problem actually. If you put a double integral, there's no dx here to integrate. So let me think about this thing. This doesn't work. I thought this should work. Okay. We can take as x square constant. Shit, I erased it. You're saying when you integrate y, you'll take x as constant, but then what will you keep the value as? X का कुछ value तो डालना पड़ेगा ना? Nee, see for given y, x is also changing. X square y, then what is x and y? You can't get any value there. There is no way to directly integrate on the curve actually. Let me think about that. But clear with this thing. This is faster and safer. Next one. And remember the projected length. This is going to again come in magnetic field and EMI. Two more chapters it will encounter. Next thing. We have a soap film. So someone placed a random loop of thread. The surface tension is S. Now the inner soap film is popped or removed. And we observe this thing becomes a circle. Last time I showed you a video if you remember. We observe it becomes a circle of radius r. This is the standard question. This is how it becomes. Find the tension in the ring. Find tension in the thread. Basically, the surface tension will be pulling it in all directions. Let me show you how the photo would look. Remember this photo? In that video I showed you, then you popped it. So what is happening here is the surface tension is pulling in all directions. This generates the tension in the string. The standard equation. So initially, why the loop of thread is random? That is because the surface tension is pulling in both the directions. So the thread can be in any shape. The net force is 0. But when you puncture the inner film, the surface tension from outside will pull it in equal all directions. This is what happens. Check. Others, do keep your hands on. SR, okay. There are two ways you can do. One, if you remember that standard method, take a small d theta and all do that thing. The standard one is this. Take a small angle d theta. So on this, the forces will be tension. This you must have remembered it. D theta by 2. This angle also will be d theta by 2. This is tension. The surface tension is pulling it out. What force? 2 into S into R d theta. So we can write 2 times sine d theta by 2. The vertical components will be 2 into S into R d theta. For small angle, sine theta is theta. This method is important. You see this in circular motion. You are seeing it here. You will see it in waves. You will see it in electrostatics. You will see it in magnetism. This will come at least 5-6 times. Elasticity, again, you will see this. Or alternative, right? Take half ring. So if you take FBD of half ring, then the forces are tension. This entire thing is a Sophil MS. So we know the projected length now. So the project length will give a force of 2 into S into 2R. So we can say 2T is equal to 4SR. That is also faster, but you need to know the projected length. Easy? I hope everyone remembers this. Should I show it bigger? I just scribbled it. I thought you guys will know that. This is half angle. This also will be d theta by 2. This also will be d theta by 2. So the tension ka vertical component. Do remember this thing. It's quite a common thing. Next thing. Surface energy. All clear with this?
Yes, sir.
Perfect.
1 second. Let me just go back. Yeah.
Clear?
Okay. Thank you.
So surface energy. So let's say we take a rod here. Length L. There is a surface tension S. So let's say someone is applying a force F and it is pulled slowly. This is the top view. And then your diagram becomes like this. The soap film has increased by X. And this force F will be 2 into S into L. So work done by external force here, since there's no change in kinetic energy, is change in potential energy plus change in kinetic energy here. This would be 0 since you're pulling slowly. This would be 2SL X is equal to change in potential energy. So this can be written as S into 2 into L into X. This is the total change in surface area. So you can remember like this. Change in surface energy is nothing but surface tension into change in surface area. Have a look at this. If there is force, there is always energy involved. Now let's see why you're getting more energy. Remember in the beginning of the thing we discussed, the molecules on the surface have a net downward force. So they're kind of actually in an unstable situation there. They possess more energy than the molecules inside the liquid. That means molecules on the surface possess more energy than the molecules inside. So when you're trying to increase the surface area, you're bringing more and more molecules onto the surface. So you're making the system more energetic. Clear? So we can even discuss this in that form. So when you have a surface here, there are multiple ways you can say this. Whenever you take a liquid and keep it in a gravity-free space, forms a sphere. Reason, if you look at the molecules on the surface, you can explain it in two ways. Since there's a net unbalanced force, everyone is trying to push inside. Since all molecules are identical, the shape you can form is sphere. That's how you can explain in terms of force.
What can you go back for a minute?
There's nothing there, right? There's one statement there.
Yeah, okay.
Yeah. So one way to explain this is molecules on the surface have net force towards the liquid. And by symmetry, they form a sphere. If everyone is trying to push inside, the shape you get is a sphere. But there is another way you can explain the same thing. We can also say molecules on the surface possess more energy than molecules inside. Right? Why? Because say again, due to the net, due to the unbalanced forces. Therefore, to minimize the energy, the molecules, the system will always try to have minimum surface area. Because if you have minimum surface area, you have less number of molecules on the surface. And we know from Max, for a given volume, sphere has the least surface area. For a given volume of liquid out of all the shapes, the sphere has a minimum surface area. Therefore, if you put liquid in a gravity-free space, you'll always get a sphere. On Earth, what happens because of the gravity, it does get distorted a bit, but they will try to form spheres. There's a reason you won't see cylindrical, you won't see cubic, and all these kind of shapes in water drops. Most of them try to be like spherical. like this. Let me show you how it looks. That's the International Space Station. It is wobbling a bit. You can see what is happening. He kept an antacid tablet there. So all that carbon dioxide, normally what happens is carbon dioxide will go opposite to gravity. It just tries to come out. But in this case, what is happening is like there is no up and down concept. So bubbles are just stuck. Here. So there, it does actually look spherical. Do have a look at this. Let's see some problems. These are again some standard problems. We have a drop. It's a liquid drop of radius r. Surface tension is S. This is broken into n identical drops. Find the change in surface energy. Let's get this. Easy one. No, Aryan, that's not the answer. Try. This is an easy one. This is like proper mains or bits level question. You will again encounter something like this in electrostatics. Yep. 0.6. Ishan, got an answer for this?
So
Done?
I'm solving.
Okay. Others, Arjun looks right. Yasha, you goofed up somewhere. Anika, definitely you goofed up. I know. You made that 0.6 kya? You had a very weird way of writing. You might be right. Lakshika, Hayru is getting n power 2 by 3, re? n power 2 by 3 nahi aayega, gods. Cube root, हाँ, Ishan, you're right. Sina, what is constant? Volume. So 4 by 3 pi r cube will be n times 4 by 3 pi small r cube. So from here we get small r is equal to r by n to the power of 1 by 3. Maybe you're right. Let's see. And then what is the change in surface energy? So change in energy will be surface tension into, remember there's only one surface, don't put into 2 here, into change in surface area. So this will be n into 4 pi small r square, that's the total surface area, minus 4 pi capital R square. You have to take the surface area of each bubble. So this will be 4 pi s into n into r square will be r square by n power 2 by 3. You guys forgot to take that n, I guess. You should take the total surface area of all the small drops. So into r square. So this is 4 pi s r square into n to the power of 1 by 3 minus 1. बस इतना ही करना था. Check. Clear? Next one. Easy. Remember this question, huh? I'll ask you the same question later on electrostatics like this. I will say there is a mercury drop with potential V. It is broken into n small drops. Find the potential of small drops. Question will be similar. Next thing. We have a soap bubble here of radius r. Pressure is P naught. Surface tension is S. And then someone kept a straw inside. And they started blowing air. In this process, this guy became a bigger bubble of radius 2r. Find the work done by the external force to make this bubble r to 2r. So the person whoever is blowing the air, so find work done by external to increase the radius of the bubble to 2r. Nope. There's something, one more term you're missing out, Ishan. This is also a good one. Again, this is not a tough one, but a proper bits or mains level question. Maybe if I'd given the options, you would have figured it out. But try. I'll give 30-40 seconds.
Oh,
Nahi
sorry,
yaad rahe.
I couldn't hear you. What is W?
What?
What is W? So I got disconnected.
Work done. And why is your voice so weird, Ray?
Okay.
Something happened to your mic, I guess.
Sir,
Arjun.
it's my internet's bad.
Okay. It looks
Yeah,
like half
internet's
robot
bad.
actually. Nee, Yasha, you also forgot the term. Atmosphere is also doing something, gods. Atmosphere is also doing something. Let's see. So the work done by external force, you're doing two things here. The change in surface energy. So you are responsible for increasing the surface area. Plus also work done on atmosphere. When you're pushing the bubble, you have compressed the atmosphere. So change in surface energy will be, remember, two surfaces, so 2s, change in surface area, 4 pi 2r whole square minus 4 pi r square. This will be plus work done against atmospheric pressure P naught into change in volume, 4 by 3 pi 2r whole cube minus 4 by 3 pi r cube. That is the thing. Most people forget the atmosphere because when the bubble is expanding, the atmosphere is also compressing. So this guy would be 8, and that would be 4 minus 1, 3, 24 pi s r square minus that would be plus 28 by 3 pi r cube P naught. Easy. Work done against atmosphere is what? P naught into delta V. It is an isobaric process. You're doing work on atmosphere. Don't take pressure due to the bubble.
Okay, sir. Got it.
Yeah. All clear with this? This part is important. That's what I'm saying. If you had seen the option now with P naught, maybe that would have striked. Next one. We have our parabola here. This is x square is equal to, again, we have our same problem there. Let's call it 4ay. I hope this is right. So
So it
this
is
is
not.
your
It should be y square equal to 4x.
So I would tell why.
y square is equal to 4x. There, I have some problem with this parabolas, I guess. Maybe I should just stick to that vertical parabola.
So it's right away.
Right. So we have a rod here. Rod of mass m. And there is a soap film here. So initially, right, this distance is a. The rod is given velocity v. Initial velocity is u. This is the top view, okay? There's no gravity. So a rod is placed on a smooth horizontal parabola on the ground. Initially it is given velocity u. Find the maximum distance it travels before it stops. Find the maximum distance it travels. So film का surface tension is S. Question is clear? The rod of mass m is placed on this thing. So basically, as you're stretching, the soap film will keep pulling the rod backward. So eventually it will slow down and stop. What is the maximum distance it travels before it stops? This is the top view, so you can ignore gravity. How do you do this? There are two ways you can do. One, you can do with work. I have a better idea. Tell me one thing. When this guy comes here and stops, the soap film has increased by this much. Tell me one thing. Where did you get all this extra energy from?
The initial kinetic energy of the rod.
Right? So that means the surface tension 2 into S into this area should be equal to half mv square.
Yeah,
Isn't
so
it?
just finding that area was the hard part.
Yeah. But that was easy. Ne? Let's see how to find the area. You guys forgot how to integrate. The whole purpose of integration is finding the areas. How do you find the area? See, let's say at a distance x, take a thin strip dx. So you get a small rectangle whose height is y. So the area of this strip dA will be 2y dx. Therefore, area will be integral 2y dx. This will go from 0 to x. And what is y? Y square is 4ax. So this is simply 2 root over 4ax dx ka integral from 0 to x. So that will be 4 comes out, root a comes out, and that is root x dx. That is x power 3 by 2 by 3 by 2. This is 8 root a by 3 into x power 3 by 2. This is the area as function of x coordinate. So initially, the rod was here, and this distance was a. And your velocity is u. Finally, the rod has come somewhat, I don't know how much it is. Let's say it has traveled x, and the velocity is 0. This has become the area. So the surface energy is equal to change in kinetic energy. So that will be 2 into S into the new area will be that guy, 8 root A by 3 x power 3 by 2 minus the initial area is this guy, 8 root A by 3 A power 3 by 2 is equal to half mu square. Easy?
Otherwise, you can just use that result also. No? The
Which
parabola
one?
area will be like 4/3 the one of the triangle.
Yeah, you can use it if I'm just showing you. What if it is not a parabola, some other shape, na?
Right.
So every time it won't be a parabola. What if I give you a shape like this? So
Yeah.
I'm just trying to show you a general way how to do it. And you're done from here. You'll get x ka value. That's your maximum. This is your x max. So you can just shift everything. That's it. You'll get the answer. Easy? They didn't start integration yet, right? Once they would have
But, like,
started,
this will come, I think, later on. Like,
once they would have started, you wouldn't have found this much difficult. Areas would have been like, for you guys, a piece of cake. For now, it would feel that way. Clear with this? So energy you can do with force also. Force में क्या करेंगे? This force F will be how much? 2 into S into 2y. That is equal to mass into acceleration. This will write acceleration is v dv by dx, and then you integrate. Actually, you get the same thing. You get the same equation. This will become change in kinetic energy. Dx will go to this will become change in surface energy. So you can do with the force method also. That also would have worked. Clear? Next one. Excess pressure. Excess pressure across a surface. Now let's say we have a random surface like this. Getting it? So we have a soap film like this, which is curvy, where this side, this radius of curvature is R1, this radius of curvature is R2. So this is your R1. This is your R2. So you have two different radius of curvatures. So we are trying to find, so this is inside P concave and the outside is P convex. So we want to find the difference in pressure between these two surfaces, outside and inside. So how to do this? Now the proof is really not that important, but let's see how to do. If I take a small strip here, but I can actually take this whole strip. Let's take a small strip. I can treat it like a small rectangle basically. Now see how the FBD would look. Now listen carefully. It is little to do with visualization. You have to be careful. So if you take this small strip, I'm going to exaggerate the figure. The surface tension force is acting like this. The surface tension force is pulling this guy this way. It's being pulling this way. The surface tension is also pulling this way. So basically, surface tension is pulling in all directions. Kidding? let this angle be d theta 2, let this angle be d theta 1. And this radius is r1 and this radius is r2. So on this thing, if you look at the side view, it just looks like a circle, right? And the forces would look like this at an angle. Surface tension here. That will be how much? And remember, this is d theta 1. We have done this right now today only. So this will be d theta 1 by 2. And this will be d theta 1 by 2. Right? But remember, what is this length here? This length is r2 d theta 2. So this force is actually surface tension S into r2 d theta 2. Getting it? Into 2. So these two vertical components would be 2f so that is the one side view. The other side view, if you look at it, how to show you the green ones, okay? Another side view. Meaning that would have looked like this. I will also draw this also like this only. This is the green ones. Let's call this thing F1. This angle would be d theta 2. This angle will be d theta 2 by 2. This F1 will be 2s into r1 d theta 1. So basically,
In
these
the
guys.
first one you have taken the angle is d theta 1, but the force is in r2 and d theta 2. Is that right?
Yeah, because देखो ना, what is surface tension for? Surface tension into length, na? The length should be this length, isn't it? This
Okay.
force is acting because of this angle, right? When you look at the side view.
Yeah, I get it.
Are you getting this thing? Yeah. So this guy will generate a downward force of, let's call it F2, to F2 sine d theta 1 by 2. These two guys will generate a net force of 2 F1 sine d theta 1 to d theta 2 by 2. Please have a look at this. Are you getting what I was doing there? It's like this thing, say. Think of like this. If you can see my screen, right? This is a sheet here. If you see, there is one surface here and there is one surface here. There are two surfaces. So one view I'm showing you like this, another view I'm showing like this. So when you look at it like this, doesn't this look like just an arc? So इसमें force कितना होगा? Surface tension into this arc length, which is r2 d theta. But the force will be pulling this way, right? So now if I combine all this stuff, pressure convex minus pressure concave into the area of that strip should be equal to 2f1 sine d theta 2 by 2 plus 2f2. It's okay, derivation, don't worry too much about it. So area of the strip would be P convex. The final result is more important. P concave. The area of the strip you can treat as a small rectangle, R1 d theta 1, R2 d theta 2. This guy would be 2. F1 is how much? 2s rd 2s r2. F1 is this, na? 2s r1 d theta 1. For small angles, you can write that as d theta by 2. And there's one more 2 will come. Plus 2 into 2s R2 d theta 2. For small angles, you can write this as d theta 1 by 2. P convex minus P concave, you end up with 2 will cancel. 2s 1 by R1 plus 1 by R2. That's your formula. This is for a soap filler. But we should have proved for single surface, we can write. For single surface, I'll show you example how this works. P convex minus P concave will be S into 1 by R1 plus 1 by R2. This is a better formula. Single surface is a better one. You can always double for a soap filler. Do have a look at this. You can note down that. Clear? Let's see some examples on this. Now, if you take a liquid drop, now in a liquid drop, there's only one surface. So here P convex is inside. This is inside, P concave. This convex is outside. So we can say P inside minus P outside is, what is the formula? Now see, for a liquid drop, if you look at the radius of curvatures, this is also R, this is also R. Both are R's only. So basically R1 and R2 are two radius of curvatures in the perpendicular direction. This guy would be S by 1 by R plus 1 by R. 2S by R. We also call this as excess pressure. The excess pressure in a liquid drop is 2S by R. If you take a soap bubble, if the pressure outside is P naught, the pressure here would be P naught plus 2S by R for a single surface. The pressure inside will be P naught plus 4S by R. For every surface, the pressure will increase by 2S by R. So here the excess pressure is 4S by R for a soap bubble. So these are the standard results. Clear? Now, if I take some other shape, for example, if you take a cylindrical bubble, so if you take a cylindrical surface, this is one radius of curvature. This is another radius of curvature. So here R1 is R, R2 is infinity. Getting it? A cylinder will have one radius of curvature is infinity, straight line, and another radius of curvature is R. So example, right? So in this case, it will be P in minus P outside would be S 1 by R plus 1 by infinity. So in a cylindrical surface, the excess pressure is only S by R. Example, it would look something like this. Let's say if you have two glass plates and if water is stuck between them, this is a water between two glass plates. That's actually a cylindrical meniscus. If you look at this is how the surface looks. So this looks like a bubble P naught here. So here, this surface would be P inside. So basically, that's what I said. If you say inside, outside, you'll get confused. If you write in terms of concave and convex, you'll understand. So if you see, this guy is the convex side, and this guy is your concave side. So P convex will be P inside. And so that is P naught minus P in will be S by R. So actually pressure inside that liquid will be slightly less. And because of this, the atmosphere actually try to compress the plates. If you want to separate the plates, you need to apply some pressure in order to separate them out. Do keep your cams on during the session, right? You need to use washroom or something, you need to just message me and you can go. But if you keep it off for more than 3-4 minutes, you'll be kicked out of the classroom. Clear with this? The cylindrical thing? So remember that for cylindrical bubbles, the excess pressure is S by R, and that too inside will be less than outside. If the same thing had been mercury, mercury would have bulged like this. This is mercury between glass plates. So in this case, this guy would have been excess pressure. So this is P naught. This will be P naught plus S by R. So be careful. Where R is this radius of curvature. So for liquid drop, it is 2S by R. Soap bubble, 4S by R. For cylindrical thing, it is S by R. If it is any other random surface they give you, this is the general formula. S by 1 by R1 plus 1 by R2. Clear? Let me ask you one more. Let's say you have a parabolic soap film. So this is 0, 0, and this is our favorite y square is equal to 4x. So outside is P naught. Okay. So what is the pressure just inside this point here? Let's call this point here A, 0. Let's call this point A. What is the pressure just inside the surface point A? What is the pressure here? I shouldn't say it's a parabola actually. Let me see whether I can draw that properly. It's like a cylinder, but a parabolic thing. Let me draw it again. Wait. It is like this. Yeah, these diagrams I'm always bad at. You're getting it is flat actually, it is going inside. How do I draw that? Wait, I'll do one thing. I'm pretty bad at this, Ray. You're getting how is the surface? It's like a cylindrical surface, but the other side is flat. It is just going inside. It's like parabolas are placed on one on top of another. Actually, I can draw like that. Perfect. There. I got it. So this was my 0, 0. So it is a flat thing. This shape is your parabola. This is your y square is equal to 4ax. This is your x-axis, and that would be your y-axis. So we have a point here A, which is at this point here, A, 0. No, find the pressure just inside A. Outside of the pressure is P naught. Today I learned how to draw parabolas with a straight. There is a formula. Remember I taught you in circular motion. What? What do we need to find here? Basically, I need to find the radius of curvatures, isn't it? What is the formula? 1 plus?
dy by dx whole to the power 3 by 2 by d square
Yep. dy by d whole square whole to the power of 3 by 2 by d square y by dx square. Yeah, the radius of curvature. This is the radius of curvature. So this is one radius of curvature, R1. The other radius of curvature, R2, is infinity because it's a straight line. That's why I wanted it to be flat. If it is a paraboloid, you'll get again two radius of curvatures. It will become confusing to do it. Actually, I could have done that also. That would have been interesting. But it's more of a max question. Let's not get into it. Then you are done. What is excess pressure? So PA would be P naught plus S by R1. You can just differentiate that function and substitute x is equal to A, 0 and you'll get the answer. Clear? So they could give you different shapes. SNA every time you'll get a sphere. That's why the formula will be useful. Mains and bits may generally won't touch that. Clear? Let's see one more. Let's see a question on this. Take a break. We'll catch up at 7 o'clock. We'll continue from there. Any doubt so far? Please ask me. This formula, right? You can refer circular motion gun notes in case you forgot. I derived this formula also. Radius of curvature. Where are you? Here. This is the mathematical method. Page 99. Clear? Any doubts? Anything you want to ask so far? Take a break. Come back by
Sir,
7.
can
then.
you send me the notes
Yeah.
of circular motion because I just joined right now?
Chalega. Ping me after the class. I'll forward it to you tonight.
All right, sir.
Concave side has more. Concave side has more pressure. While writing the formula, why we have convex minus concave surface. Did I do that?
That's
I
right.
goofed up. I goofed up. My mistake.
Alright.
Chalo, good thing you told.
Actually, I was thinking कि I understood wrong or something, but then I thought that
नहीं,
I just
मैंने
have
लिखते
to.
समय मैंने यहाँ पे चेंज कर लिया. Whole thing went up actually.
Oh,
In my mind, I was thinking convex only. Yeah, you're right. You're right.
and sir,
Hmm.
जो आपने diagram बनाया था, could you like explain that to me? Like in this
Which
one,
one?
which derivation था? Convex वाले का derivation sir,
इसका?
का.
Hmm.
Yeah, that was like outer bulge, right? That surface.
हाँ. Outs a bulge.
Okay, okay. All right, thank you, sir.
Hmm. Think of like your head का scalp ना.
हाँ, got it, got it. Okay,
चलो.
right.
चलो back by 7.
Yeah.
चलो, comes on everyone. So let's say we have a bubble and we have one more bubble inside. This is R. This is 2R. Outside is P naught. So we have concentric soap bubbles. Okay. Let's call this point A. The first question, find pressure at point A. Second question, if P naught is 0, that means outside is vacuum and the inner soap bubble is punctured. Assume isothermal conditions. Assume temperature is constant. Find the new radius of the bubble. You're getting, if you pop this bubble, that air will leak, right? So the bubble radius will change. What is the radius of the new bubble? Let's get this. Get this, everyone. Yeah, there is no soap. This is all air. Yep, 6s by R, that is there. Get the second part. How do you do that? So the first part is easy. So pressure here would be P naught plus 4s by radius. Radius is 2r. So remember, the pressure at A, right, is always, if I call this point B, the pressure inside is always pressure outside, P naught plus 4s by radius. Pressure at A will be pressure outside, that is PV plus 4S by R, which is P naught plus 6S by R. Clear? Clear, no, Monica? Do adjust your camera, Monica, can't see you. Others? What about the second question? Now, if I pop this bubble, the air will leak and the radius of the one bubble will change. So what is the new radius? Tell me one thing, when you pop this bubble, what remains constant? What remains constant?
Total volume of air inside.
Volume, seriously?
Number of moles.
Moles of air.
Number of moles will remain constant. Now try PV is equal to nRT, kTg. So initially the condition is outside is vacuum, P is 0. So this pressure will be, let's call it P1, let's call this P2. This is R and this is 2R. Now for this gas P1, the equation will be P1. What will be the volume? So P1 will be 4S by 2R. 2S by R. P2 will be P1 plus 4S by R. 6S by R. So P1, V1 is N1. R is the gas constant. I'll write RG into T. P1 is 2S by R. What is the volume? Now be careful. It is 4 by 3 pi 2R whole cube. Into N1 RGT. You're getting it? You should take the volume between them, na? You can't take the entire 4 by 3 pi 2R whole cube. And for the second gas, which we write P2, V2, the inside volume, this is N2 RGT. This equation is for the gas between R and 2R. This is gas up to 0 to R. So P2 will be 6S by R. The volume will be 4 by 3 pi R cube. Will be N2 RGT. So when these two combine and you get a one big bubble, let the radius be R dash. Outside is vacuum. So for this equation will be V dash, V dash. Number of moles will be N1 plus N2 RGT. So this will be 4S by R dash. Will be P1 V1 plus P2 V2. Substitute, you will get R dash from here. I'll leave the working team. Clear? You know P1 V1, you know P2 V2, substitute there and you'll get the answer. Next one. Any doubts on this? Next one, this is a theoretical question. If you have a big bubble, R1, and if you have a small bubble, R2, and if you connect them with a pipe, the air will flow from where to where? Air will flow from where to where? What is the pressure here? P1 is P naught plus 4s by R1. What is the pressure here? P naught plus 4s by R2. So whoever has smaller radius will have more pressure. P2 is greater than P1. So air will flow from small to big. Be careful, huh? Just a theoretical question. Whoever has smaller radius will have more excess pressure. Clear? Yeah. Happens. Be careful. Next thing. Clear, na, Vartika? Neil? Vidyut? Swastika? Abhinav? Great. Next one. We have a soap bubble. Outside the pressure is P naught. You connected a thin pipe. This is a pipe of length L and radius R. Outside is also P naught, and this is a soap bubble. Surface tension is S. And this radius is capital R. Now, the pressure inside is more than outside, and eta is the quotient of viscosity of air. So because the pressure inside the bubble is more here, the air will start leaking out of this pipe into the atmosphere. And because of this, the bubble ka radius will decrease. Find the radius of the bubble as function of time t. The initial radius is R. Viscosity and surface tension. Question is clear? Yeah, let's get that. How to do? Remember the Poiseuille's equation? dV by dt is pi delta P R power 4 by 8 eta L. So because of the difference in pressure difference, the volume is leaking. We have to start from there. Cube root of 64 pi. Aryan, if you put T0, shouldn't you get initial radius? You're not getting. That's the simplest way to check. If you put T0, your answer should give you R. Then let me help you with the initial part. Check out the things. At any time t, let the radius be x. Isn't that how we always start? So pressure inside will be P naught plus 4s by x. The pressure outside is P naught. So the excess pressure is 4s by x. So the formula is now dV by dt is pi delta P small r power 4 by 8 eta L. So dV volume will be, we know volume is 4 by 3 pi x cubed. So dV will be 4 pi x square dx. We'll put a minus sign because it is decreasing. Pi delta P is 4s by x small r power 4 by 8 eta L. Four pi cancels off. Bring that x here. It will become x cube dx. This will become minus r power 4 by 8 eta L dt. Surface tension. Integrate. Limits will go from r to x. This will go from 0 to t. The x power 4 minus r power 4 by 4 is minus s small r power 4 time by 8 eta L. There you get x ka value from here. Check. Easy. So you can use Poiseuille's equation and the surface tension ka excess pressure, and you can relate both of them. Clear? Any doubts on this? Next one. The limits, yeah, we have to be careful. Next thing. Two soap bubbles of radius R1 and R2 coalesce. Coalesce meaning stick together. That is a technical word for it. Meaning find radius of the interface. Let me show you how it looks. Find alpha, beta, gamma. Like this. So two soap bubbles got stuck like this. This radius is R1. This radius is R2. This is your interface. So this also will have its own radius. I want you to find that R. And now at this interface, if you draw the angles, this angle will be alpha This angle will be beta. And this angle will be gamma. Find alpha, beta, gamma. The diagram would have looked like this. There are 3 bubbles here, but 2 bubbles would have been like this. How do we know which interface is curved? Think about it. Whoever has more pressure will be concave. Whoever has less pressure will be convex. Who has more pressure? Whoever is a smaller radius. So in this case, I didn't tell you what is R1, R2. So that is fine now. Choose any one. The science will take care of it. Let's get this one, everyone. Find the radius R. And find alpha, beta, gamma. Lakshika, that is right. Let's see. Right, Yasha. Nee, Ali, that is wrong. Ishan, you're right. Adrit, Abhinav, yeah, we all got it. See, the first part was actually easy one. If I take this as P1, this is P0. So P1 will be P0 plus 4s by R1. P2 will be P0 plus 4s by R2. And for this interface, P1 minus P2 should be 4s by R, excess pressure. Because this P1 will think this itself is a bubble. So have the values here. So 1 by R is 1 by R1 minus 1 by R2. Standard formula, you need to remember this. Example, if R1 is equal to R2, then R will tend to infinity, meaning it becomes a straight line. If you have 2 equal bubbles, this is how it would have looked. What about the angles? Now look at the angles there. If you draw this part, FBD, this is how it looks. So at this point, the pressure P is pushing this way. At this point, the pressure is P. At this point, the pressure is P. The 3 pressures are equal. Why? If the pressures are not equal, the soap solution will keep moving till the pressures become equal. Now you tell me, if you have three equal forces acting at a point, and if it is in equilibrium, what should be the angle between them?
120.
120. Bus. So alpha, beta, gamma are 120, independent of R1, R2. You take any soap bubble, you always send 120. So basically, at the interface, of three surfaces, all the three pressures which are equal are keeping are in equilibrium. Clear? So that is again one important result. These are bits and CET level questions. Check it out. Clear? Next one. Oh, you don't got the 120 thing now? Yasha, clear na? Aditya? Anusha? Ishan, clear na? Ali? Great. Next one. Let's get this one. Point A is here. Meaning, if you look at the diagram now, side view, it would have looked like this. So this is that wall. The liquid is like this. You're getting how is the 3D view? So it's like a slope. This is the front view, what they're showing in the question. So he's asking find the pressure at point A and he's asking find H. I can even ask you one more thing here. Radius of curvature at point A. Let's get this. The first part is actually easy. Take a minute. Right, Ishan. That is right. Yeah, that is fine. Let's have the second part. Let's see. Root T by G. Okay. The first part. Now see, the pressure is actually the easy one, because at the bottom level, what is the pressure? Here the pressure is P naught. So here also pressure is P naught. So if you go to a height h, the pressure here should be P naught minus rho g h. Instead of going from the top, go from the bottom. And at this point, if you take the radius of curvature, so that looks like a soap bubble here, where this pressure is P naught, and this side is that it looks like this. Inside is P naught, and the point A is outside. And we know P convex minus P concave. In this case, it would be P naught minus PA is that excess pressure, which is 2S by R. So P naught minus PA is rho GH is equal to 2S by R. This is how you can find the radius of curvature. 2S by rho GH. Now, how to find the height actually? You have to find the h ka value. Root T R rho GH. Okay, let's see. See. Draw the FBD of the liquid. Okay, we are writing only the horizontal forces. Let's see only the horizontal forces. First thing, this surface here is surface tension, which is S into L. So let this length be L. This height is H. And on this surface, we have a atmospheric pressure that is P naught. And we also have the Volcker force this way. Now, the force due to the wall, we have done this in fluid mechanics, if you remember. The force due to the wall is nothing but the pressure at the center of mass into area. Pressure at center of mass into area. Pressure at center of mass will be P naught minus rho g h by 2. You're going from the down. Huh? This is h by 2. Remember, at the base, the pressure is P naught. And what is the area? L into h, the projected area. And what is the force due to the on that curve? The atmosphere is pushing this way. The projected area will be this. So the force on that curved surface is atmosphere pressure P naught into projected area.
So I didn't guess this one. How is the projected area that side?
For this curve, what is the projected area? Horizontal projection. That's a rectangle, right? There are actually two projected areas, but we are interested only in the horizontal forces.
Okay. Okay, sir.
We are taking only the horizontal forces. Getting it? This is a F curved, let's say horizontal. This is only the horizontal component. The reason why we're not taking vertical component is because I can't calculate mg. Now, since it is in equilibrium, what are the forces? So F wall is pushing it. Surface tension is pushing it S into L, and the atmosphere is pushing P naught into LH. So F wall will be P naught minus rho GH by 2. LH plus SL is equal to P naught LH. P naught will cancel. You end up with rho GH square L by 2 is SL. Therefore, H is equal to 2S by rho G. Or check. Please ask me if you're confused. The atmosphere is pushing, everywhere like this. So we only take the horizontal projection. Clear? A bit of a fluid mechanics, a bit of a surface tension. That's about the excess pressure in a bubble. Any doubts on this thing? Rehan, clear with this? Abhinav, Arjun,
Yes, sir.
Neil, Udayan, got this? Swastika, Maulika, where are you? Got disconnected, I guess. Great. Next thing. Contact angle. Now remember in the beginning we discussed there are three different force profiles. The one inside, the one on the surface, the one on the edge. So till now we played with the molecules on the surface. Now if you look at the molecules on the edge, you will notice something. So on this edge, the forces will be. So this is due to the water. The adhesive, these are called cohesive forces. Cohesive forces is the force between like molecules. These are adhesive forces. This is between unlike molecules. Next time when you buy Fevicol, on top of it read the marking. It will be written like adhesive karke. Yeah. So now, if you look at the forces on this, the force profile, the adhesive forces, cohesive forces will be like this, almost at a 45 degree. The cohesive forces will be like this. If the F adhesive is greater than F cohesive cos 45, these are called wetting substances. And you will notice the liquid actually starts climbing the surface. This is how you would see. The liquid actually climbs up. In real life, we don't see it much because it's actually very small rise. You need to have a very small radius to observe this. If F adhesive is less than F cohesive cos 45, these are called non-wetting substances. Meaning simple reason, the force between the like molecules is so strong, they try to go away from the solid. This is a case of, mercury and glass. This is like water and glass. So if I show you how it looks. You can see the surfaces there. The left side is a colored water and the right side is a mercury. Look at this thing. This is mercury and red colored water on this thing. If you observe here, this is the water there which spreads off. So here, the cohesive forces are stronger adhesive forces are stronger than cohesive. So the liquid will, get attracted to the surface more. It will spread out. So here for water, adhesive is greater than cohesive. So the liquid spreads out. It will try to get in as much contact as possible because attraction is more, spreads over the surface. Whereas if you see mercury here, this is non-wetting. The liquid tries to be together. So in this case, the cohesive is greater than adhesive. So mercury will try to stay together. So mercury will not spread on a glass. Mercury tries to stay together. Getting how this thing looks? Clear, everyone? Now, if you try to draw the angles, so this is how we define the contact angle. Angle between the tangents to the liquid and solid, away from the liquid or towards the liquid. Let me show you a diagram that will be better. It's called contact angle. Meaning, now see, at the point of contact, right, you can draw two tangents. One, you have to draw the tangents away from the liquid towards the liquid. So for the liquid surface, this is away from the liquid. For the solid, this is away from the liquid. So this is the contact angle. Are you getting it? Meaning, see, at this point now for the liquid, this is towards liquid. At this point for the solid, this is towards liquid. This is contact angle. So draw both the tangents for the liquid and the solid away from the liquid or towards the liquid. Let me show you one more. Suppose if you have like this and the liquid is like this. So at the point of contact, that is this guy here, this is the point of contact, the one in the red. So if you draw a tangent, this is towards liquid. So this is away from liquid. For the solid, this is towards liquid. This is away from liquid. This is your contact angle. If you take a shell filled with liquid, so the point of interface, this guy, away from liquid, this is contact angle. If you have a shell and the liquid is outside, away from liquid, this is contact angle. Suppose if you have two curved surfaces like this, this is for the solid, this is for the liquid, this is a contact angle. Please have a look at these examples. So whenever you want to find a contact angle, at the point where the liquid and the solid touch, draw two tangents. Both should be away from the liquid or towards the liquid. So if theta is acute, these are wetting substances. If theta is obtuse, these are called non-wetting substances. Have a look at this. Yeah, have a look at this. Clear with this? All clear with the contact angle concept? No. Let's see. Capillary action. I'm sure you studied this in biology. The trees, get water to the leaves through capillary. So how does this work? So when you say capillary, right? Capillaries are actually thin pipes. Let's see what is the concept. Take a container. Introduce a thin pipe into this. And we observe the liquid level actually rises. Now we need to see why it rises. When a capillary is placed in a liquid, we observe the liquid level rises. In real life, we don't see this because that rise is actually very small. In order to see this, you need to have a very thin tube. So here R is the radius of the capillary. Theta is the contact angle. Rho is the density of liquid. S is the surface tension. So let's draw FPD of the liquid. Now in HSC, this is an important proof. HSC, they'll ask you, find the height of a capillary action using the force method, using the pressure method. There are two methods actually. I'll show you both, but let's look at this thing. So when you draw the FBD of the liquid, this is how it looks. I'm exaggerating the figure. So if you look at this, we measure the height only up to this level. We ignore this liquid in this meniscus. We ignore this. No, the surface tension force will be which way? The surface tension force will be along the surface, like this. Can you imagine a trampoline? Remember what did we say? The entire surface acts like a membrane. So the top surface will act like a trampoline. So that surface tension is pulling it up. This angle is theta. So the vertical component will be 2 pi r s surface tension ka vertical component cos theta. And this would be our mg. This is straightforward. So we get 2 pi r s cos theta should be equal to the weight of the liquid. Two pi r s cos theta. This should be rho, area of the cylinder pi r square h into g. So we end up with h is equal to 2s cos theta by rho gr. Standard formula, you need to mug it up. Now, the reason why we don't see this in real life is because the surface tension of water is 10 power minus 4. Denominator mein density is 10 power 3. Gravity is 10. That comes to almost 10 power minus 8. That value is so low, it becomes almost negligible. So in order to see this properly, you need to have a very thin pipe in order to compensate for that. Let me show you how it looks. Look at this diagram. That formula is what? H is equal to 2s cos theta by rho g r. So H is proportional to 1 by r. You can clearly see the liquid level, see here. Did you notice? This radius is quite big, so capillary action is negligible. This is a negligible capillary action. Because the radius is so big, we really didn't see much. Yeah, the color is so weird, right? Better. Here you can clearly see it dominates. Kepler is more visible. You can see that height, how much you got. This is quite a thin tube. The smaller the radius, more the height. So in order to see a Kepler reaction, you need very thin pipes. Smaller the radius, more the Kepler reaction. Clear? So that is one formula using the force method. The alternate method, that is the reason why you don't see Kepler reaction in real life, even though it exists. We use the pressure method. The force method is so nice, but okay. Again, draw the FPD of this. So in this method, this curve which is there, what we do, we assume this is a part of a bubble. We can assume the liquid surface acts like a part of a sphere. Liquid surface is a part of an air bubble. That means for a person standing here, if you ask him, what do you see? He will say, there's an air bubble inside the liquid. That is what he will feel. So this is point A. So pressure at A will be P naught minus 2S by R. Remember, P naught is inside, R is outside. Remember, R is the radius of curvature. So this is radius of curvature. This is small r. So don't get confused, both are different. R is the radius of curvature of the surface, whereas small r is the radius of the pipe. And we know here this angle is theta. So this angle will be theta. This is the relation between them. R cos theta is equal to small r. This itself is a question in the exam. Find the radius of curvature of the surface, r by cos theta. Most people write the radius of the pipe as radius of curvature. Don't do that. Be careful. Once you got this, you're done. So this height is h. The pressure at the base should be P naught. So PA plus rho GH should be the pressure on the surface, which is P naught minus 2S by R plus rho GH, which is P naught. So we get H is equal to 2S by rho G capital R. We can replace that capital R with small r, you end up with 2S cos theta by rho G R. Same formula, doesn't matter which way you do. This is the pressure method. Have a look at this. Clear? That is one thing. Now, if you observe here, right, this theta can be negative also. For mercury and all, the liquid will be actually depressed. Okay, so with this, we'll wrap up for the day. So next class when we meet, we'll continue from here and we'll do more problems on this. So next class, we will wrap up the chapter. I think maybe first half, it might finish it off. If we finish off a little early, then we will start off with elasticity, a little introduction. At capillary, we do have a few good questions. So we will work it out that. Okay, so with that, we'll wrap up for the day, right? And I hope everyone has given the test. The next test will be online tomorrow. So any doubts, anything in today's class? Any other doubts that you have, you're free to ask or else you're free to leave. So take care, stay safe. I'll see you guys again next week on Wednesday, same time. So any doubts in today's class, first you can ask.